Hello guys, this is Camille Gamarcha, the in charge of discussion for this group.
Hello guys, I am Janelle Rosette Chipaneda, the in charge of the procedure in this group.
Hello, this is James Rhett Aying, in charge of the table on this video.
Hi, this is Brian Chadiap Alba, and I'm in charge in the Coulomb's law diagram.
I am Wilrose Castellano, in charge for the analysis of this group.
Hi, I'm Jeter Paul Malyari, and I am in charge in making the conclusion in our group.
Hello guys, my name is Justin J. Parando and I'm in charge of the editing of this group.
In this diagram, the ruler is used to measure the distance between the two charges. Putting the two charges nearer decreases the distance between them. The two circles represent the two macroscales. The blue-colored one represents a negative charge while the red-colored one represents the positive charge. As we move the two macroscales, notice that the force also changes. The arrows of the two charges will be used to identify if the force is either attraction or repulsion. If the arrows are facing inward, it means the force is attraction. If otherwise, it means repulsion. The two boxes below the ruler is where the charge would be adjusted. Going left would give a negative value and going right would give a positive value.
In our laboratory experiment 1, we need to verify the principles that governs the Coulomb's law for electrostatics, and the only material that we used is the FET simulator. So first, we opened the FET simulator and selected macroscale. By this, we easily identified the distance, changed the charges, and recorded the forces between those charges. Second thing that we do is we set a constant distance between the charges. The distance was used in all 5 trials in Table A. Third, we set the charges, and as we go through the trials, we are increasing the value of the charges, and we also recorded the force applied between those charges. For Table B, the charges were held constant, and we also used that in all 5 trials in Table B. As we go through the trials, we also made the distance between the charges increase and also recorded the forces applied between those charges.
Tables which consist of 5 trials. In Table A, the distance between the charges are held in constant, so each trial, the distances are the same. In Trial 1, the Q1 is positive 1, while Q2 is positive 2, with a constant radius of 4 times 10 raised to the negative 2, with which the forces between the charges are 11.234 newtons. In Trial 2, Q1 is positive 1 and Q2 is positive 3. With the same distance, the forces between the charges are 16.852 newtons. In Trial 3, Q1 is positive 2 and Q2 is positive 5. With the same distance, the forces between the charges are 56.172 newtons. In Trial 4, Q1 is positive 3 and Q2 is positive 6, which the forces between the charges are 101.110 newtons. In Trial 5, Q1 is positive 3 and Q2 is positive 7. The forces between the charges are 117.962 newtons. In Table B, the amounts of charges are held in constant, which each trial, the charges are the same. In Trial 1, the constant charges are positive 3 and positive 5, and with a distance of 2 times 10 raised to the negative 2, the forces between the charges are 337.33 newtons. In Trial 2, the charges are the same, and with the distance of 3.5 times 10 raised to the negative 2, the forces between the charges are 110.052 newtons. In Trial 3, the charges are the same. With a distance of 4 times 10 raised to the negative 2, the forces between the charges are 84.258 newtons. In Trial 4, with the same charges and the distance of 6.10 raised to the negative 2, the forces between the charges are 37.448 newtons. And in Trial 5, with the same charges and the distance of 7.5 times 10 raised to the negative 2, the forces between the charges are 23.967 newtons.
The Coulomb's law for electrostatics states that the force between two small charged bodies acts along the line joining them and is directly proportional to the product of the two charges and inversely proportional to the square of the distance between them. Coulomb's law for electrostatic could also be stated as F equals K Q1 times Q2 over R squared, where F is the electric force, R is the distance of separation between two charges, Q1 and Q2 are the charges carried by objects 1 and 2, and K is the constant. The constant K is equal to 9 times 10 raised to 9 Newton meter squared over C squared.
To verify the Coulomb's law for electrostatic using PET, we manipulated the value of variables to describe the relationship of charges and electrostatic force of attraction with respect to distance between them. We analyzed the electrostatic force of attraction is increasing if the charges are increasing in constant distance, and also it is greater if the distance between charges are lesser. So the magnitude of the electrostatic force of attraction between the 2 point charges is directly proportional to the product. The magnitude of charges and inversely proportional to the square of the distance between them. If the charges have the same sign, electrostatic force between them is repulsive. If they have different signs, the force between them is attractive.
Rising the distance of separation between objects decreases the force of attraction or repulsion between objects, as well as reducing the distance between the point charged increases the attraction or repulsion force between them. We also imply that electrical force are sensitive to distance or displacement. We conducted that the principle that defines the electrostatic law of Coulomb stated that the electrostatic force between the two charges is directly proportional to the magnitude of the two charged objects, and that the distance between each charged object is inversely related to its square.